the same. We looked at the exercise 2 for the quiz, right? Problem number 2, is that right? Parabola question was find its vertex, and way we did it is we found the derivative and then we set it equal to 0. So question was find x that turns that derivative to 0. So when we have quadratic function with x squared, it's called quadratic, then derivative of this will be 2x plus 6, right? So this is what I'm going to write equal to 0. Then 2x plus 6. And then I'm gonna solve this by bringing the negative 6 over. So we're going to have negative 6 over 2, which is minus 3. So in this case, it's minus 3. So I have found the x coordinate of a point, which is going to be, if parabola opens up, this minimum point, the lowest point on the parabola, and we call it as vertex. And that definitely helps us to get a graph. But to actually get a graph, I need to do a little bit more, right? I need to find y coordinate of that point as well. So I guess the answer is minus 3 if we stop at that stage. But if you want to continue, then you use that number negative 3 in your function, and then calculate y that corresponds to it. So in this example, we have 9 minus 18 and then minus 3. So this is going to be equal to number negative 9 and 3 is 12. So this way I can graph this parabola that opens upwards. So here's minus 3 for x and minus 12 is for y, the vertex of that parabola. So when I do the graph, then I'm gonna have the parabola that opens upwards and goes somehow like that, and we've got the result. Also, in a college algebra class, if you remember, if you ever took it, then this last number, negative 3, or a free term would determine the intersection with y-axis, just like with line, slope, and y-intercept. With parabola also, intersection with y-axis, that number without any x, and we can see that looks like it is indeed supposed to be someplace there. So I found the graph, and that's, I guess, great to know. So we were graphing. We also looked for the asymptotes when we graphed in the previous class. Later in this class, we'll also get those, but I guess not for these exercises. So far, I just want to graph everything with no asymptotes, just to get help by using methods of graphing. Excuse me. So let me try exercise number 13. Another problem, but now we have x cubed present in it. So let us graph something that is in the same shape as a cubic parabola, which is going to be something like that, right? X cube. And I guess we don't really need any methods of calculus for this, because if I look at what function we're supposed to graph, then it'd be 3 times, actually 2 times x to the power of 3. So the shape of that curve is going to be similar, but it is actually twice farther away from my x-axis, because I have 2 times x cubed. So people say sometimes the graph is contracted. It got closer to the y-axis. So then when I finish with the graphing, when I subtract 16 from this cubic term, then the graph just goes down by 16 units and looks just like that. So here's the, I guess, old way to graph functions that we utilized in the previous classes. And you don't really need methods of calculus to graph such a cubic parabola. And my goal is to make sure that you realize it. So don't need to overdo those exercises. So as long as you're familiar with the basic graph of function y is equal to x cubed, and that's, I guess, what we already considered before, right? Then you could just use various transformations on it and produce yourself the graph that you need. Similarly, if I try to do exercise number 23, then it will deal with a graph of a function cube root of x, which is a friend of a cubic parabola, but it goes along x-axis rather than along y-axis. But in a way, it's kind of same thing. And if you would like to graph in the problem 23, the cube root extracted from x minus 1, then the graph that you have here is going to be shifted by 1 unit to the right. So this cube root function will be moved by 1 unit along the x-axis. That's what always happens whenever we have in the parentheses some number subtracted from x. Always like that. So that's good to realize, and sometimes people want to double check this. They say, is really point with coordinates 1 for x and what for y? 0 for y, right? Why is it 0? Well, because this point belongs to x-axis, because if you draw perpendicular to the y-axis, you will hit origin or point 0 on the y-axis. So pair 1 for x and 0 for y has to fit into this equation that we are working with. So if you put 0 for y and 1 instead of x, then this has to work. So if you check this out and see is 0 going to be equal to a cube root extracted from 1 minus 1, you will say, yes, it checks, because 1 minus 1 is 0, so I cube root 0, got 0. So it does pass through that particular point. So again, I didn't use any derivatives, so I didn't use calculus to graph. I just utilized transformations. Again, you just wanna not to do more than you need for the exercises. So I'd like to, from this page, I don't want to look at the next page. You see this pictures they want are using this symbol called graphing calculator. I already shown you, I guess, how to find that calculator once, but you're not supposed to worry about it in this sections. And I will, of course, show you how to find that calculator again in the next section when we need it. So section 2.2 is talking about using the second derivatives in order to get graphs of our functions. So what is this about? Well, like in problem number 13, where we work with the, where's this cubic? I just saw it. With a cubic parabola, what they do is they say that you can find the point of so-called inflection, where you can imagine the curve like a parabola that opens upwards that changes its shape with a curve that the parabola that opens downwards. So if I go back and look at exercise 13, I can see such a point here at -16. So let us take derivatives of those, let me write it, function 2x to the third power minus 16. And turns out this is being attained by taking a second derivative. So first derivative will be 2 times 3 is 6x squared. And then if I find derivative once again, right, second derivative, we get a 12x. And when I have it equal to 0, then this equation has a solution, x is 0. And indeed, when x is equal to 0, this happens that we have inflection. So we're always trying to find what x values give us those special cases. And when I say, so how do you know this point is actually -16? Well, we always find points by plugging in the function what we just found. So instead of x, I put 0, and I see that indeed y is equal to -16. That's all that's left, and that's why we can see clearly the point is here, coordinate 0 and -16. So let me get another exercise and do the whole thing, because these derivatives, they actually help me to graph. Because when you already know how the graph looks like, it's just pointless to use them, because the whole point of this is to graph. And if you already have a graph, then why do you need to worry about derivatives? So let me do the problem, let's say exercise number 15. Let me try exercise 15. That looks like another cubic function. I selected that because there is a minus sign in front. So function f of x is largest power 3, and that's actually negative with x to the power of 3 plus 3x squared. And then we'll also subtract 4. So we need to take a derivative of this function. So this is going to be minus 3x squared, right? And then 3 times 2 will give us 6 times x, and -4 disappears. So this first derivative, and then we're also going to find the second derivative. And we're gonna set both of these derivatives equal to 0, right? So it's negative 3 times 2, 6 with x, and then plus 6. So let's find those special critical points. People say they're critical points. They see when our derivative is equal to 0, right? And they factor and find when. So minus 3x is going to be factored out, and then x, and then minus 2. I say, Alex, why didn't you factor out plus 3x? We can factor out plus 3x. You will get the same exact result. Check it out if you want to. So minus 3x, I set equal to 0, or the other factor, which is x minus 2. And this will give us two special numbers. One of them is 0 for x. That's from the first one. And from the second, x is equal to 2. So there we have the two solutions. Similarly, I'll solve the second one. So I can write that minus 6x is equal to negative 6. So what is x? Well, it looks like it has to be number 1, right? Because 1 times negative 6 is still going to be negative 6. So I'm going to be graphing a function from family of cubic parabola, the one that I left here on the top. So one end of this graph must point upwards and the other end point downwards. So let us plot this function f of x, and remember, to be able to do this, I must get y coordinates of points. And I found 3 points. One of them was 0, the other was a 2, right? We just found them. 2, and the last is 1. And this should be sufficient enough to get a graph. So plug in these numbers to my original equation. That's a tedious part. But since we got lucky to deal with so nice numbers as 0, 1, and 2, then looks like the calculations will also be nice. Like in the case of number 0, we just get a negative 4 because this part is all 0, so they disappear. So next is here, 3 times 2 squared, and then minus 4. So what do I get? I get a minus 8, right? And then add it with 12, and then subtract 4, and this is 0. Well, my favorite number. Okay. And the last one was number 1. So 1 cubed plus 3 times 1 squared, and then minus 4. So it looks like then we have 1 and 3 is 4. Actually, minus 1 and 3 is 2. Minus 4 is negative 2. Great. I'm ready to get a picture. I'm ready to graph this cubic function. So first of all, I will put these pairs. 0 for x, minus 4 for y. Someplace here, right? 0, negative 4. Next pair is going to be 2 for x and 0 for y. So this is someplace here, 2, 0. Okay. And then another point, coordinates 1 for x and negative 2 for y. So x is 1, y is negative 2. That's right in between. So you can say, oh, that's a line, Alex. No, it is not a line. This is a cubic function. Remember, the cubic function is what we just found. So I need to be real careful when I graph it. So what is that we're producing in here? Well, let us do this carefully, and I have to get negative x cube. So the shape of it will go down here and up there. Remember, whenever we have a minus in front of the third power of x, then the graph will look like that. So what does that mean in terms of my particular case? Well, it has to go down like that. Just we have here, you see? And then I get parabola that opens up, like part of parabola that opens up. So this is not a line, absolutely not. So what I just used is techniques of second derivative. So whenever I have this 0.1 as a 0 of second derivative, we get so-called inflection point, where we change our graph in such a way that instead of parabola that opens down, it starts to open up. And of course, this maximum, the largest point, and the lowest, the minimum, is also here. People call them as local minimum and local maximum, because actually this function has no maximum because it goes infinitely up. Same with the minimum, it just keeps going. This arrow says goes down, so it definitely falls lower in y coordinates than this level, but that wiggly part gives me local minimum and local maximum. And we just produced a graph that could only be done using methods of calculus, using those first derivative and second derivative as well. And I think that this is pretty amazing. And I also recall that's pretty much the same thing we did last time as well, right? So looks like the procedures did not change at all. We just repeat the same story. First derivative equal to 0, second derivative equal to 0. And this enables us to graph lots of functions that we couldn't graph before. This is a power of the method. So I just graphed one with an x cube. So why don't I graph another one that has x squared and repeat same steps? X force. How about 27? Here's the graph that I want to make with the force power of x. Now it's going to have both ends that point in the same direction. They will both point upwards, right? Because it's from family of parabola-like functions like x squared or x to the fourth or x to the sixth power. All of these even powered functions have both ends going either up, or if it's minus x to the fourth, down. Well, in 27, where our function is x power of 4 minus 4x power of 3 and plus 10, we have positive x to the power of 4. So both ends will resemble to what I have above, will point upwards. And now after first derivative and then the second derivative. So take derivative of x power of 4, we get 4, and then power of x is 1 less, right, x cubed. Then 3 times 4 gives us 12. So it's same exact formula that we keep using for finding derivatives. So I found first derivative, now second derivative, I continue the process. Now I multiply 4 and 3 and get 12x squared. And then minus 12 times plus 2 is negative 24 with x. So that was a good start. I need to make this equal to zeros, both of them, and solve equations. So I no longer care for a derivative piece. I just care about solving these equations. So 4x squared is what I factored. We get a x minus 3 in the parentheses equals to 0. Either 4x squared is 0 or the parentheses is 0, right? And we got our solutions. So solutions are plus 3 and 0. But notice that x to the power of 0 kind of appears twice, right? So we say that order of that solution is 2. We'll see what that is going to bring us when we graph. Because here's x minus 3 by itself. If it be squared, then the order is also 2, but not for this one. So we'll keep this in mind and we solve the other piece. And I can factor this again, take out 12x and have x minus 2 in the parentheses. So looks like 12x is 0 or x minus 2 is 0. So please notice that x is equal to 0 appears again. And that's what this order 2 actually brings us with. So it appears again, and that's okay. So now we see why this was order 2. So I'm going to graph. I'm going to need to have y coordinates of these. Looks like 3 points. We have a 0, right? We have also 2 and 3. So they created nice exercises for us. We should appreciate that. So what happens when we have 0? Well, I need to find f of 0. Next is f of 2. One say, why did you use them? Well, because we just produced 2, right? We produced 0, and we produce also 3. So I need to put f of 3. So these are special points that I need to picture on the coordinate plane, and that will help me to graph this fourth degree function. So I'm plugging in zeros and the others. So when I put zeros instead of x's, well, then everything will be very nice, and you just get 10. And this is a good start, right? It's 10 because this stuff cancels, it's zeros. Then with a 2, you could use calculator because you don't have to do this just by hand. The calculator is a helpful tool that should be used. Of course, you get some big number. 16 and 32 is going to be 48, and 10 is 58. Please double check it. Did I get it right? 3 to the 4th plus 4 times 3 cubed and plus 10. Actually, I didn't get it right because I wasn't careful, because I had to put a minus sign. Do you see the minus here? It's a minus. You say, yes, Alex, I see minus, but I have a plus. So I want to make sure that this is actually minus here. So it's not 58. What is this? 16 subtract 32 is negative 16 plus 10 is minus 6. That's different. Now, let's do this again. 81, right? 9 times 9. And then we minus from this 27 times 4. So notice that's 3 cubed could be factored out. 3 minus 4 is negative 1. So it's negative 27. So you can see this is just minus 27 and 10 is minus 17. Well, let's plot the fourth degree function. First point is 10. When x is 0, I got 10. That's my starting place. So that was positive 10. Why did I put 0? It's 10. Right? When x is 0, then y is 10. So I put 10. Then we have two more values to worry about. One of them is 3 and the other is 2. So when x is 2, then y is negative 6. Someplace say here, negative 6. That's for x equal to 2. And I say, Alex, you have different scales on x and y axis. Yes, that's for convenience, so we can better see what's going on with the graph. Because it's up to you how you select your scale. I just marked those numbers so everybody can see what they actually are. And now the key part, both ends must go up, right? So how can I achieve that? Well, looks like starting from this point, I have to somehow go up, right? Just like that. Please notice that this is a 0.0 of my second derivative. I say, oh, so what? It was also 0 the first derivative. Yes, but since it's 0 the second derivative, then the behavior of function changes from using like a parabola that opens upwards. I'm now changing and have like parabola that opens downwards. See, we inflected our curve at point 2, at point 0. Now, also we inflected it at point 2, so the behavior changes to the parabola that opens up. So it's going to keep opening up because there's no more 0 second derivative. How about that? That's a very interesting wiggly structure here. And again, without using our derivatives, we'll probably in no way be able to get the graph of those polynomial functions. And I hope now you're convinced that sections 2.2 and 2.1 are just dealing with pretty much same thing. So I don't want to look at the next page. I'd rather just take a little look at the section that has fractional powers, fractional functions. They look like ratios. That's why we call them rational functions. So here they have a graph of a fractional function. And what I just want to look at today, denominators. So I'm looking at x minus 2 and x plus 3. Notice that neither one of them can be equal to 0 because I don't divide by 0, right? So I can say x plus 3 is not equal to 0 and x minus 2 is not equal to 0, right? So x cannot be equal to 2 and neither x could be 3. So x is 2 and x is minus 3 are exactly invisible walls. We call them as vertical asymptotes. So the function approaches them but doesn't intersect. And I can get them very fast just looking at denominators and make sure that my denominators are not equal to 0, because when they're equal to 0, then asymptote, vertical asymptote, will appear. So today I just want to start talking about this section. I just want to look at this vertical asymptotes idea. So let me do another exercise with finding the vertical asymptote. So I'm looking at section 2.3, and I can do problem like number 1 exercise. It says, how about if you try to find vertical asymptote? So they don't say the graph, just look at the fraction here in exercise 1. I can write it as y, f of x or y, it's the same thing, doesn't matter for us. So it's 2x minus 3 over x minus 5. Well, all I care is about denominator. So domain says that denominator is not equal to 0, and therefore x is not equal to 5. So it turns out when x is equal to 5, I'm going to get that so-called vertical asymptote. If I try number 7 exercise, it will be done in the same exact way. I will hear only about denominator. In fact, this denominator I can possibly factor with numerator x plus 6 over x plus 1. So one can say x plus 6 will cancel? Yes, it will. But when I care about domain, I will say that neither x plus 6 is equal to 0, nor x plus 1. They cannot be zeros because we don't divide by 0. Even though, yes, x plus 6 will get canceled, but still number -6 is out of domain, just like -1. So can you please tell me what be the issue with domain in exercise 2 as a quiz? So just like I did in the previous 2 exercises, tell me what x cannot be equal to. And eventually it will give us vertical asymptote. So what x is not allowed to be, and that's all we need for today, for the little quiz.